Hey everyone! So far, in the practical part of the course, we've used OpenAI's GPT models to discuss model inputs and outputs, chat memory, the LLM chain, and the LangChain expression language. Now that you've acquired solid experience with LLMs, I hope you can see that these are powerful, state-of-the-art models, trained on vast amounts of data and answering questions on various topics. The models are rapidly becoming better and more knowledgeable, but training them takes a lot of time, so the data available to LLMs inevitably has a cutoff date. Additionally, out-of-the-box models can't answer questions about proprietary information, such as your company's data. But imagine if there was a way to combine the power of LLMs with custom data. We could use LLMs to analyze and summarize results, tag files, perform question answering, and more. In this lesson, we'll discuss 3 ways to achieve this: prompting, fine-tuning, and retrieval augmented generation, the topic of this entire section. But let's start from the beginning. The most straightforward way to provide a model with personal data is to feed the information directly through prompting. This means inserting the data as a system message, a set of few-shot examples, a chat history, or however appropriate. You then pass these prompts to a model, as we've done many times. This approach is quick and easy to implement. Moreover, LLM's increasing context windows allow for passing even more information. Bear in mind, however, that feeding long paragraphs each time a model is invoked could also result in a time-inefficient and token-consuming application facing decreased performance, so use this technique with caution. And what about the second approach for supplying a model with custom data? Fine-tuning involves continuing to train a pre-trained language model, such as GPT-4, on your custom dataset. This significantly differs from the prompting approach, since fine-tuning directly interferes with the model's inner workings, adjusting the weights of the neural network's connections to better align with the nuances and patterns of your data. A fine-tuned model comes with the following benefits. It's trained on vast amounts of data, generally responds to better quality, requires less context and, therefore, shorter prompts, and could result in shorter response time. Of course, it's not all good news because this process comes with some disadvantages. Fine-tuning a model requires more effort and resources. These include time and computational power. The process could last as long as several days. A substantial dataset, since fine-tuning a model only makes sense if it has plenty of examples to learn from, and expertise in machine and deep learning for managing and optimizing the fine-tuning process. Although intriguing, fine-tuning falls outside the scope of this course. Instead, our focus in this section will be on the third technique for combining a model with custom data: Retrieval Augmented Generation, or RAG for short. This is an approach whereby we keep large amounts of embedded data inside a database and retrieve only the portion necessary for answering the specific user question. Throughout the rest of this section, we'll provide an overview of the Retrieval Augmented Generation technique, introduce each of its components, and then move on to the intriguing bit, coding. There's a lot to cover, so hold on tight and let's jump straight in. Hey everyone! In the last lesson, we discussed different ways of integrating custom data into a model. The first way was to prompt the data directly. Although fast and straightforward, we realized this approach is only suitable for smaller datasets. The second method we covered was fine-tuning a pre-trained model, like GPT-4, which continues the training by fiddling with the neural network's connections and weights. This technique typically results in a faster, lower-priced, and more accurate model. Still, fine-tuning has the disadvantage of being more involved and resource-consuming. In this section, we'll study the third method of combining LLMs with custom data: Retrieval Augmented Generation. Let's begin. A RAG application typically consists of 3 major parts. Indexing. preparing the data and storing it in a specialized database. Retrieval, retrieving only the documents most relevant to a user's request. And generation, taking the user request with the retrieved documents and employing an LLM to produce a context-aware response. Let's examine these components individually. Indexing is an integral part of a RAG-powered application, encompassing the following key processes. First, load custom data from various formats to a standard LangChain document format. Second, split the document into smaller chunks to ensure it fits the LLM context window limit. Third, embed the text in the documents so that each chunk has its own vector representation, capturing the semantic meaning of the text. And finally, store these vector representations in a specialized database called a vector store. Now that we have the data loaded, split, embedded, and stored, we can proceed to the next component, retrieval. Retrieval is responsible for taking a user query, searching the database for the documents most relevant to the query, and retrieving them. They're then ready for the next step in the RAG sequence, namely the generation. During this step, the user query and the retrieved documents are fed to a language model as a prompt. The model then constructs a response and sends it back to the user. And that is Retrieval Augmented Generation in a nutshell. It relies on prompting the most relevant parts of an otherwise huge dataset. This bypasses the need to feed the entire data as a prompt and the resource-heavy task of fine-tuning a model. But just as with any approach, RAG 2 has some downsides. One disadvantage of this method is the increased latency of the response due to retrieving information in real time. Additionally, the quality of the retrieved documents heavily influences the model's response. If the retriever doesn't spot the relevant information, the model will respond poorly, even if the answer is in the data. All right, I'll wrap up this lesson here. What follows is a discussion of how each step of the RAG technique, indexing, retrieval, and generation, is realized in LangChain. Afterward, we'll open our Jupyter notebooks and implement a RAG-powered application using LangChain's expression language. Thanks for watching, and see you soon. Welcome back, everyone. In the last lesson, we provided an overview of the Retrieval Augmented Generation technique and learned that it consists of three main parts: indexing, retrieval, and generation. The first part, in turn, comprises the following steps: document loading, splitting, embedding, and storing. We'll dedicate this lesson to the first two steps: document loading and splitting. Let's get into it. Document loaders in LangChain are classes responsible for taking a data source, a PDF, HTML, JSON, or virtually any other standard format, scraping its content, and saving it as a list of document objects. Document is a class in LangChain used to store a piece of text and its associated metadata, such as page number, document title, and document subtitle, among others. Converting data from any format to a uniform structure might sound straightforward, but document loaders are an essential and involved component of a RAG application. This standardization means that all files are handled identically in later stages, despite the diversity of their original formats. LangChain supports integration with many file formats and can load data directly from various file storage platforms, such as Google Drive and Dropbox. The practical part of this section demonstrates how to load content from PDF and docx files. You're then encouraged to experiment by applying the same process to other file extensions and noting the different metadata extracted from these files. Okay, so we have our files loaded as a list of documents. What's next? This initial list of document objects has several issues. First, there's no restriction on how much content a single document stores. This can pose a problem later in the process, as there is a restriction on how much content we can pass to a large language model. If the content we try to prompt exceeds the model's context window limit, we reach an impasse. But even if the content does fit the limit. Consistently passing large files to the model leads to another drawback: excessive token consumption, which substantially increases the application cost. Therefore, we need a mechanism that splits the document objects in a process known as document splitting. And here we reach another, more subtle issue. Studies have shown that language models perform better if they're fed chunks of documents covering a single topic, instead of large texts encompassing various topics. This means we need to find a mechanism that not only splits the data into chunks to decrease the document's length, but also ensures that each chunk is centered around one topic. As we'll discover in the upcoming lessons, performing these splits is often a nuanced process. Later in this section, we'll study several document splitters that LangChain offers. All right, so far we've covered the process of loading a text file and splitting it into meaningful chunks that fit the context window limit of a model. We now want to create a chatbot that answers user questions based on the information stored in these chunks. To answer the question most efficiently, without needing to go through each split individually, we seek a mechanism that locates the one semantically closest to the user question. The technique for that is called embedding, and will be the next lesson's topic. See you there! Welcome back! In the last lesson, we started our RAG discussion by focusing on the first two components of the indexing part: document loading and splitting. We realized the need for a mechanism that swiftly identifies the most relevant chunks for a given question. Enter document embedding. Embedding a text is a process whereby a language model converts it to a vector, effectively capturing its semantic meaning in a numerical format. With the help of these vectors, we can perform similarity searches efficiently. This likely sounds unintuitive, but it's an approach that works impressively well for LLMs. Let's study a simple example and conceptually discuss the meaning behind vector representations. Imagine we have two vectors, each representing a chunk of text, one containing the keyword star and another sun. When positioned on a coordinate system, these vectors would sit closely together because they have close semantic meaning and are often used in the same context. Conversely, segments with spaghetti and bolognese are distant from the earlier pairs, yet closely related, as these terms frequently co-occur but seldom align with star and sun. Good! Let's now position a third pair of text chunks on the coordinate system. I've chosen ones containing the keywords ice cream and sorbet. Their vector representations would sit closer to the ones of spaghetti and bolognese because they're both consumables. In contrast, they would sit further from the vectors representing star and sun. Let's now consider the following user question. Can you give me a quick dinner idea to prepare this evening? The first step is to embed this user question. That is, we use an embedding model to create a vector representation of this query. When positioned on the same coordinate system, this vector would sit closest to the chunks containing spaghetti and bolognese, since they're most frequently seen in the context of dinner compared to the rest of the keywords. Analogously, the vector would sit a bit further from the texts about ice cream and sorbet. Unsurprisingly, it will find itself furthest from the vectors representing the texts containing star and sun. So, when asking the model for dinner ideas, we'd first retrieve the chunks related to spaghetti and bolognese. Next in line are the ones related to sorbet and ice creams. And at the end of this list are the splits related to our sun and other stars. All right, no problems so far. But when I say that two vectors are close to each other, what do I mean exactly? How do we measure this closeness? Some frequently used distance functions are the dot product between two vectors, cosine similarity, or Euclidean distance. OpenAI recommends the second one, so that's what we'll explain briefly now. To understand cosine similarity, we'd first need a quick refresher on the dot product, a topic discussed in greater detail in our mathematics course. So consider two vectors, A and B, placed at the origin of a coordinate system. Geometrically, the dot product of two vectors is calculated by taking the product of their magnitudes and the cosine of the angle between them. Upon rearranging this equation, we can express the cosine of the angle between the two vectors as the dot product between A and B divided by the product of their magnitudes. For simplicity, OpenAI's recommended embedding function normalizes the vectors to length 1. This means that the denominator on the right-hand side becomes 1 for our equation, so we can remove it to avoid clutter. Now recall that you can also find the dot product algebraically, namely by multiplying the coordinates of the vectors pairwise and then taking their sum. That is, if A and B are two-dimensional vectors with coordinates AX, AY, and BX, BY, then their dot product will be calculated as follows: AX times BX plus AY times BY. Okay. The last thing we must recall is how the cosine function itself behaves. For simplicity, let's position vectors A and B in the first quadrant of the coordinate system. If they happen to be parallel to each other, the angle between them becomes 0 degrees. Using a calculator or a trigonometry table, you can ensure that the cosine of 0 degrees is, in fact, 1. If we now increase the angle between the vectors to 30 degrees, the cosine decreases to about 0.87. Increasing the angle to 45 degrees, we obtain a cosine value of about 0.70. Rising to 60 degrees, the cosine becomes half. And once we reach a right angle, the cosine drops to 0. So we conclude that as the angle increases, the value of the cosine function decreases. Returning to our example, the vector representations of two semantically close chunks will subtend a smaller angle, resulting in a high cosine value. The more distant two words are, the larger the angle between them, and the smaller the cosine value. As you can imagine, 2 dimensions typically aren't enough to capture something as complicated as the semantic meaning of a text. Languages are complex and intricate, so vector representations live in hundreds, even thousands of dimensions. To be more specific, OpenAI's currently recommended embedding model is Text Embedding 3, which comes in small and large versions. They create embeddings with as much as 1,536 and 3,072 dimensions, respectively. But considering we're expressing something as complicated as human language, this number is insignificant. All right, in the practical part of this section, we'll embed text chunks and compare different dot products. But before that, we still need to cover the topics of document storing and retrieving. See you in the next lesson. Welcome back, everyone. Let's start with a quick recap of what we've discussed so far. Recall that we first load the data from any of LangChain's supported formats. LangChain then ensures the data is stored as a list of document objects that keep the text and the corresponding metadata. Next, we split the documents into smaller chunks, each containing meaningful information and fitting the context window limit of the chat model. The embedding process then transforms each text chunk into a vector that encapsulates its semantic essence. This vector form proves particularly advantageous for efficient document search. All right, after obtaining the vectors, we need a place to store them. A database where highly efficient searches are key. Conventional relational databases won't do the trick because they're not optimized for this purpose. If you're familiar with SQL databases, you know they're designed to retrieve values that precisely match a given query. For example, consider the query, select user ID equal to 12 from the student info table. This will search for the student corresponding precisely to user ID 12. It won't retrieve IDs similar to 12. But this approach to querying is not suitable for our similarity search use case, where we don't look for an exact match. Doing so would be the equivalent to searching the exact question in the vector database. Instead, we need results semantically related to our query. And that's what vector databases allow. Okay, we've already gone from loading to splitting to embedding and eventually storing the embeddings in a vector store. This is where the indexing part ends and makes way for the following essential component: retrievers. As the name suggests, retrievers are part of the RAG chain responsible for retrieving the most relevant but also diverse chunks of data. The diverse part is important here. Although we need to retrieve the semantically closest chunks to the query, we must ensure that each chunk contributes new and valuable information to the table. Picture a simple example in which one of the chunks in the vector store is inadvertently replicated. Next, imagine an incoming user query for which we are required to retrieve the two semantically closest chunks. If the chunk in question happens to be the one semantically closest to the query, then we'll fill in the slots with the original text and its duplicate. Therefore, rather than supplying the model with new information, the second retrieved chunk will only repeat the information from the previous one. So both relevance and diversity are essential in the RAG procedure. So far, we've covered what the R in RAG stands for. Now, we introduce augmented generation, a process in which user input and retrieved text are combined and fed into a large language model to generate contextually aligned responses. And that's it for the theoretical part. I hope you now have a good understanding of the different components encompassing the RAG technique. I'm sure that by the end of this section, any doubts you may have will be cleared up as we dive into the practical aspects. We'll begin with the document loading and demonstrate how to load a text file in a PDF format. See you in our next lesson. Hey everyone! Welcome to the practical part of this section, where we'll cover document loading in LangChain. I'll show you how to load files with PDF and docx extensions. LangChain offers a plethora of document loaders in addition to these two. Once you learn the procedure, you can work with any supported extensions. With that said, let's jump into coding. First, open the Anaconda prompt. If you're in the base environment, ensure you conda activate LangChain env. In this environment, pip install the PyPDF library, which we'll need to load PDF files. Once the installation is complete, pip install the docx to text module, which we'll utilize when loading docx files in the next lesson. Once done, locate and download the PDF file from the Resources tab next to the video. Open a fresh Jupyter notebook running on the LangChain environment kernel. Ensure the notebook and the PDF file are placed in the same folder, which will ease the implementation in a second. In the first cell of the file, perform the following imports: from LangChain community, .document loaders, import PyPDF loader, and then import Python's copy module. Next, create an object called loaderPDF as an instance of the PyPDF loader class. Pass the name of the downloaded PDF file as an argument. If the notebook and the text document are in the same folder, passing only the name of the document rather than the full or relative path to the file would be enough. Let's now open the PDF and inspect its content. It's a transcribed version of 2 lessons from 365's most sought-after course, Introduction to Data and Data Science. The lessons are Analysis versus Analytics and Programming Languages and Software Employed in Data Science, all the tools you need. We'll use these lessons to eventually create a chatbot that accepts a student question as an input, retrieves the relevant information from the transcript, and returns an answer based on this information. Upon inspecting the file, many new lines have appeared during the transcribing process. Since we can't easily deal with them in a PDF file, we'll do so in Python. One of the available methods for PyPDF loaders is load. Apply it to the loaderPDF object and store the result in a variable called PagesPDF. the result is a list of documents. Applying the length function to this list, we find 6 in total, each corresponding to a page in the PDF. A parameter called page content stores the allocated portion of the text. The second available parameter, metadata, stores the metadata for a specific chunk of text. In our case, that's the document's path and the page number where the particular text is located. All right, let's now discuss the new lines introduced during the transcribing process. One disadvantage of having so many redundant new line characters is that they consume tokens. As you know, token usage is monetized. Of course, our example is relatively small. We're using the text of only 2 lectures from a single course. Leaving the new line characters wouldn't affect the bill much. Still, imagine we wanted to use the text of all lessons from all courses on the 365 platform. The new line characters would accumulate quickly, and removing them would become noticeable. That will be the goal for the rest of this lesson. Let's create a new variable. Call it Pages PDF Cut, and use copy.deepcopy to clone the Pages PDF list. I won't go into much detail here, but we need a deep copy, in this case, to avoid overwriting the original file. Feel free to delve into this topic in more detail on your own. Okay, we now want to change the page content of the documents inside Pages PDF Cut by removing all new line characters. How can we do that? First, retrieve the page content of the first item in the list, indexed 0. We can apply the split method since the resulting object is a string. You might recall from our Python Programmer Bootcamp course that this approach creates a list of all words in the sentence, omitting the new line characters. Now, surround this expression with parentheses and set it as the argument to a join function. Apply the function to a string storing only a single whitespace. This line of code joins all words in the list with the character in the string, serving as a separator. We now must apply this procedure to all documents in the list. Using a for loop, create an iterator that picks every document. Then extract the page content and set it to match the expression we've made. Substitute the first element of the Pages PDF Cut with the iterator I. Run the cell and display the variable. We see that the new line characters are removed everywhere. Great! Let's evaluate the significance of this processing step by taking the page content of the first document in the list and comparing its number of tokens to the ones from the original text. Display both texts on the screen. Now visit OpenAI's Tokenizer website. Copy-paste the uncut paragraph. Note the number of tokens. Copy-paste the text with all new line characters removed. We obtain a number significantly smaller than the first one. This helps us appreciate the improvement we've made in terms of token efficiency. Note, however, that this is a text modification you'd rarely need to make. Each text file you work with requires special care and pre-processing. In this example, the new line characters cluttered the text rather than contributed to the formatting, so we're forced to remove them. In the more frequent cases where the text is well formatted, the new lines can later be used to split the text into meaningful chunks. All right, next we'll continue the discussion on document loaders, focusing on loading a file with a docx extension. See you there! Welcome back, everyone! In the previous lesson, we studied the PyPDF loader in LangChain. Additionally, we pre-processed the loaded text by removing all new line characters because they didn't contribute to the formatting of the text. In this lesson, we'll solidify our knowledge of document loaders by demonstrating how to load a file with a docx extension in LangChain. The relevant document is in the resources complementing this lecture. Start by opening a clear Jupyter notebook running on the LangChain environment kernel. We already installed the library necessary for loading files with a docx extension, So we can directly start by typing from LangChain community .document loaders import docx to text loader. Note that in the class's name, it's essential to have the letters D and L capitalized, the word to written as the integer, and the word text shorthanded to txt in lowercase. Import the class and then define a new variable. Call it loader docx as an instance of the docx to text loader class. As usual, it's easiest to have the text file in the same directory as the notebook. This allows us to set the file name as an argument. After opening and examining the file, you'll see it contains the same 2 lectures from the Introduction to Data and Data Science course. All right, now create a new variable. Call it pages docx and set it equal to loader docx.load. Load the document and display the pages docx variable. We get a list with only one document object this time, storing the entire text from the file. Scrolling down, we see that the stored metadata is only the path to the file, without the page number. Still, the page number would not be advantageous for our use case. Since the text represents a transcript of a video course, a student asking a question wouldn't reference a specific page. All right, in the next lesson, we'll discuss document splitting using the most straightforward algorithm, splitting into chunks based on the number of characters in a chunk. Thanks for watching. Hey everyone! Welcome to this series of lessons on document splitting. As we've discussed, splitting a document into semantically meaningful chunks is essential in the RAG process. It helps reduce the text size, ensuring it will fit a model's context window limit, and segments the text into chunks of specific topics, which improves the quality of the chatbot's responses. LangChain offers various algorithms for splitting a document. Let's begin with a splitting governed by a predefined number of characters, which means we obtain chunks of roughly equal sizes. Before jumping to coding, however, I think we should discuss this idea conceptually through a simple example. Imagine we're given a text containing 1,500 characters. Please pay attention to the fact that we're referring to characters, not tokens or words. We can now design a splitter separating the text into chunks with a maximum of, for example, 500 characters each, resulting in 3 chunks of equal sizes. In that way, we've reduced the size of the documents from 1,500 to 500 characters at the cost of increasing their number. From 1 document, they become 3. Another parameter we can specify is the chunk overlap. Chunk overlap corresponds to the number of characters overlapping between subsequent chunks. Let's continue our example. Consider our 1,500 character document split into chunks of 500 characters each. We can now study how the number of splits will change if we introduce a chunk overlap of 50 characters. So, the first chunk remains unchanged. The second chunk, however, begins with the last 50 characters from the first chunk and continues by taking 450 characters from the rest of the text. Similarly, the third chunk begins with the last 50 characters from the second chunk and continues by taking 450 from the rest of the text. Since we still have some text left over, the fourth and final chunk begins with the last 50 characters from the third split and then takes the remaining 100 from the text. Therefore, introducing a chunk overlap increases the number of splits, but it has the benefit of including context from the previous split to the next, thereby introducing a smoother flow between the chunks. Okay, we've covered the conceptual part of the character splitting technique. It's time we realized it in code in the next lesson. Welcome back! In the previous lesson, we introduced LangChain's character text splitter through a simple example. Now, we'll apply this knowledge to our practical use case. Let's get to coding. I've set up a new Jupyter notebook using the LangChain environment kernel. Beforehand, I added a short piece of code which should be familiar to you. I've imported the docx to text loader. created an instance of this class with the name of the file as an argument, loaded the pages from the document, and created a for loop removing the new line characters from the text. Displaying the page content of the first and only document in the list, we see that the code has loaded the document and successfully removed the new line characters. We'll also need the number of characters in this text, so let's use the built-in length function. Perfect. Next comes the splitting procedure. Return to the first cell and import the character text splitter class from LangChain text splitters. At the bottom of the notebook, initialize a new variable. Call it character splitter and assign it as an instance of the mentioned class. The first parameter we can specify is separator. By default, separator is set equal to 2 new line characters, a common way of separating titles from paragraphs. But we removed these characters from our text, so let's set the separator equal to an empty string and continue exploring other class parameters. We'll look at chunk size and chunk overlap. Let's set the size of the chunks to 500 characters at maximum. By default, the value of the chunk overlap is set to 200 characters. So, if you don't want any overlap between the splits, specify this explicitly. All right. One of the methods that this class implements is split documents. It takes a list of document objects, such as the pages list, splits them accordingly, and returns a new list of documents. Store the result in a variable called pagesCharacterSplit. Display this new object. We see a list with many more documents stored inside. Returning the length of the list, we find it 17. How so? If we divide the length of the original text by 500 characters in a chunk, we obtain 16 completely filled-in chunks and a 17th one filled in halfway through. If we multiply the fractional part by 500, we get the number of characters that should be stored in the 17th document. Let's check by retrieving the last document from pagesCharacterSplit, selecting its page content, and retrieving the length of this text. And that's precisely what we get. All right, very good. Let's now introduce an overlap between the chunks and see how this affects the results. I'll set the corresponding parameter to 50 characters. Run the cell and perform the split anew. Display the page content of the first element in the list. We see the first chunk ends with, so let's clear this up, shall we? First we will start. The last sentence ends abruptly, but we expect it to continue in the next chunk. Displaying the split under index 1, we find that it begins with, let's clear this up, shall we? First, we will start with analysis. Indeed, the final few characters of the first split were added as the beginning of the next one. To avoid abruptly ending chunks, sometimes even mid-word, we can set the separator as a period, indicating the end of a sentence. Redefine the character splitter again, and split the text anew. This time, the number of documents in the list is a bit higher. If we retrieve the number of characters from the first document, we'll understand why that is. The length isn't precisely 500, but slightly less, at 444. Retrieving the page content, we see that this time, the paragraph doesn't end abruptly, but at the end of the sentence instead. You might also notice that the last period in the chunk is missing in each split, because separators aren't included in the content. As an exercise, you can create a for loop that appends a period at the end of each chunk. All right, excellent job, everyone. I hope you've grasped the idea of splitting by characters in LangChain. But you might wonder, how do we know that a single topic isn't spread across several chunks, or that one chunk contains several topics? The truth is, we don't. And that's why the character text splitter isn't the only one LangChain offers. In the next lesson, we'll discuss another way of segmenting text using a markdown header text splitter. See you there! Hey, and welcome back to this discussion on document splitting with LangChain. In the previous lesson, we introduced the character text splitter, the simplest among splitters, which segments text based on a separator, maximum chunk size, and chunk overlap. The splitter did an excellent job of reducing the size of the documents, but as we discussed, we had no control over the topics they covered. That's why we'll now study another document splitting technique based on splitting concerning headers. Let's get into it. Open a fresh Jupyter notebook using the LangChain environment kernel. Before we start coding, let me introduce you to the Markdown formatting so we're all on the same page. Enter a new cell and navigate to the drop-down menu, which is currently reading Code. Change this option to Markdown, allowing us to write formatted text in the cell. For our lesson, what's important to know is that in the Markdown language, different heading levels are represented with various number of hash signs. The bigger their number, the lower the heading level. Let's try it out. Write a single hash sign followed by an interval and the text heading 1. Hit Shift and Enter. We get a heading big enough to serve for a title. Now continue with 2 hash signs followed by an interval and the text heading 2. Finally, do the same with the text heading 3, preceded by 3 hash signs and an interval. All right. You can now see that heading 2 is a subheading to heading 1, and heading 3 is a subheading to heading 2. Good. We can move on to actual coding. Import the familiar docx to text loader class and the new Markdown header text splitter class. Create an instance of the loader class and load the pages from the document. These couple of lines should already be familiar to you. Now display the pages variable. It's a list storing a single document object. Proceed with the following. Create a copy of the docx document and append the number 2 to the title to distinguish it from the original. Open the file. Next, enter a new line above the first lecture. Type the name of the course, Introduction to Data and Data Science, and precede it with a single hash sign and an interval indicating a main heading. Now navigate to the title of the first lecture and include 2 hash signs followed by an interval. This will indicate to the splitter that this is a second-level subheading. Finally, navigate to the title of the second lecture and do the same. Save and close the file. Redefine the loader docx variable with the new file. Then run the cell to load the document anew and display the updated list. We can see the hashes now appear in the page content. So, what's the next step? In a new cell, initialize a Markdown splitter variable and set it as an instance of the Markdown header text splitter class. One of the available parameters is headers to split on, a list of tuples, each storing 2 strings. Let the first element be a single hash symbol. The second string should correspond to the label of the first level heading. I'll go with course title. Let's do the same for the second tuple, changing the number of hash symbols to 2 and setting the label to lecture title. The next step is to create a new object that stores the pages from the split. Call it Pages Markdown Split, and set it equal to Markdown Splitter dot split text. As an argument to this method, add the first and only element of the pages variable and extract its page content, namely the document's entire text. Let's see what the new variable stores. We found a list with 2 document objects. Each document comes with a page content and a metadata parameter. Metadata is a dictionary with 2 keys, course title and lecture title, the strings we specified earlier in the definition of the splitter. For the first lecture, their respective values are Introduction to Data and Data Science and Analysis versus Analytics. The second document in the list corresponds to the second lecture from the same course, so the value of the lecture title key differs. Notice that the course and lecture titles are no longer part of the page content, since the split was based on these headings. Great! I think now is a good time to stop. But our work isn't done. We still need to remove the new line characters from the text. Additionally, if a lecture happens to be too long, we might want a mechanism that splits individual lectures, preserving the metadata that keeps the course and lecture titles. I'll leave both tasks to you as an exercise. Feel free to study LangChain's documentation and experiment with other splitter classes, such as the token text splitter or the recursive character text splitter. There's so much to explore. So, we've learned how to perform the first and second parts of the indexing process, document loading and splitting. I'll see you in the next lesson, where we'll continue with the third part, embedding the texts. Hey everyone! In the practical part of this section, we learned how to load and split the data. Next on our agenda comes embedding it. Remember, embedding refers to representing a chunk of text as a vector. This allows each chunk to live in a vector space where we can determine the semantic closeness between vectors. Earlier in this section, we explored the concept. Now, let's put it into practice. I've designed a new notebook that imports the docx loader and two text splitter classes. Next, I created an instance of the loader class and used it to load the text from the document. Then I initialized a markdown header text splitter object and used it to split the text into lectures. I implemented the familiar for loop and used it to remove the new line characters cluttering the text. Finally, I created a character text splitter object and utilized it to split the text further within each lecture, preserving the course and lecture title information. Let's check if the variable pages character split stores the expected documents. Indeed, we get a list of documents, each with page content and metadata storing the course and lecture titles. Okay, now to the embedding part. Return to the beginning of the document and add the following line of code. From LangChain OpenAI, .embeddings, import OpenAI embeddings. Since we'll be using embeddings from OpenAI, we need to run the code responsible for setting up the API key as an environment variable. As usual, I'll do this at the beginning of the notebook. Return to the bottom cell and initialize a new object. Call it embedding as an instance of the OpenAI embedding class. We can specify the embedding model we wish to work with through a parameter called model. Let's go with the following. All right. As a toy example demonstrating how embedding works, we'll apply the available embed query method on 3 individual strings. The first one is the page content of the 4th document in the page character split list, part of the analysis versus analytics lecture. Next, we'll embed the page content of the 6th document in the list, also a part of the same lecture. Since these chunks are extracted from the same lecture and are positioned close to each other in the text, we expect them to have a solid semantic relation. The 3rd string we'll embed is the page content of the 19th document in the list, this time part of the 2nd lecture in the docx file. We expect this lecture to be loosely correlated with the previous 2. To realize this plan, initialize a new object, call it vector1, and set it equal to embedding.embeddQuery. Pass as an argument the page's character split list, fetch the element at index 3, and extract the page content. This piece of code will use OpenAI's embedding model to create a vector representation of the content stored in the 4th element of the list. Now copy this line and paste it 2 times. Rename the 2nd variable to vector2 and let it store the embedding of the string at index 5. Rename the final object to vector3 and change the index from 3 to 18. Let's study these objects, starting with vector1. We obtained a list of floating numbers forming the vector representation of the 4th element in the list. The embedding model we're using produces vectors with a dimensionality of 1,536. The lengths of the other 2 objects, vectors 2 and 3, are also the same. Therefore, we can apply the dot product to each pair of vectors and quantify their similarity. import the NumPy library, which offers a suitable method for that purpose. I'll do this at the beginning of the notebook and alias the library as NP. Return to the bottom of the notebook. Apply NumPy's dot method with arguments vector1 and vector2. Remember that these were splits from the same lecture. We get a value of approximately 0.88, quite a high result. But to appreciate this number, we need another result to compare it with. Let's therefore apply the dot product to splits from different lectures, namely to vectors 1 and 3, and then to vectors 2 and 3. We obtain two new, very close results of about 0.80. This number is smaller than 0.88, showing that vectors 1 and 2 are further apart from vector 3 in this vector space. Finally, for this lecture, let's ensure that the vectors created with OpenAI's embedding function have a magnitude of 1. Let's calculate this using NumPy's linear algebra module. Invoke the norm method. Norm is another word for magnitude, and pass vector 1 as an argument. We obtained 1, as expected. Rerun the cell, this time with vectors 2 and 3. We again obtain decimals rounding to 1. All right, excellent job, everyone. Keep in mind that in this lesson, we embedded only 3 of a total of 20 chunks. Therefore, we're starting to feel the need for a vector database to store these embeddings. That will be precisely the topic of our next lesson. Can't wait to see you there. Welcome back, everyone. We dedicated the last couple of lessons to loading, splitting, and embedding documents with LangChain. In the previous lesson, we applied embedding to only 3 of all 20 chunks in the page's character split list. Our task for this lesson is to embed and save all chunks in a vector store. Ready? Let's get to work. In the notebook, I've prepared a familiar code. I've set up the OpenAI API key as an environment variable, imported the loader, markdown header, and the character text splitters, imported the OpenAI embedding class, loaded the pages of the docx file, split it based on the course and lecture titles, removed the newline characters from all texts, split it based on the number of characters using a chunk overlap and a period as a separator, and created an instance of the OpenAI embeddings class with the desired embedding model. I've also checked the number of documents stored in the page's character split list. Now, rather than embedding each document separately, as we did in the previous lesson, we'll utilize a vector store and embed all documents simultaneously. LangChain supports integrations with many vector stores, and you can browse them all in the Integrations menu. The vector store I've chosen for this course is Chroma. Start by pip installing the Chroma database package in the LangChain environment. Give the installation some time to complete. Afterward, return to your Jupyter notebook and refresh the Python interpreter by restarting the kernel. This will ensure the interpreter recognizes the new library. At the beginning of the notebook, import LangChain's Chroma class. All right, we're ready with the setup for this lesson. Now let's initialize a new object, vector store, and assign it as an instance of the Chroma class. We want this vector store to keep all 20 documents from the page's character split list and their vector representations. This is achieved by invoking the FromDocuments method. The parameters we'd need to specify are the following: documents, embedding, and persist directory. The first parameter expects a list of the documents we want to add to the vector store. The page's character split variable is precisely what we'll need. Next, the embedding parameter expects an instance of the LangChain's embedding class. That would be the embedding function that creates the vector representation of the documents we've just fed. Finally, to save this collection locally, we need to specify the persist directory parameter. You can select any directory on your computer, but I'll store the database in a folder called Intro to Data Science Lectures, located in the same directory as the notebook. Note that persist directory is not a required parameter. If you don't specify it, the vector store will only exist until the kernel is restarted or shut down. We'll demonstrate shortly that persisting a vector collection allows us to retrieve it even if we restart the kernel. This avoids embedding all tokens anew, which is beneficial since, as you know, embedding is a token-consuming process. All right, let's run the cell. Locate the folder titled Intro to Data Science Lectures, where the Chroma vector files are kept. Since the documents and the embeddings are stored locally, we should be able to create a new vector store object using the files from this folder. Let's do so. Return to the notebook and create a new variable called vector store from directory as an instance of the Chroma class. Next, pass the values of two class parameters, persist directory and embedding function. As you're already familiar, persist directory is a string indicating the path to the database. We also need to pass the embedding object used to create this vector store initially. This is necessary because the documents in the vector store can be updated, or new ones can be added. So, the vector store needs to know which embedding function to use to maintain consistency and accuracy in the representations of existing and newly added documents. Additionally, suppose this vector database is used as part of a context-aware chatbot application. In that case, it should be able to embed the user's input with the same embedding function to find semantically similar documents. So, let's reiterate. The vector store object was created by applying Chroma's FromDocuments method, using an embedding function to embed all documents in a list, and specifying a local directory to store the files. The vector store from directory object was, in turn, created from an existing database by assigning it as an instance of the Chroma class. All right, excellent job, everyone. I'll stop the lesson here. In the next one, we'll continue our exploration of vector stores by inspecting and managing their content. See you soon! Welcome back to our discussion on vector stores and managing their content. In this lesson, we'll show how to add, update, and delete documents within the vector store. Let's get to work. I've created a new notebook where a few lines of code are pre-implemented. These are setting OpenAI's API key as an environment variable, importing the OpenAI embeddings, Chroma, and document classes, creating an instance of the OpenAI embeddings class, and creating a vector store using the files stored in the folder we called Introduction to Data Science Lectures. You can pause the lesson and implement the code at your own pace. Once done, run all cells in order. During our previous discussion, you might have been curious to see the embeddings themselves. After all, I only claimed we've created them, but never actually showed them to you. So let's quickly show how to access them. Apply Chroma's get method on the vector store object. As a result, we retrieve a long dictionary containing information for each embedding. What's helpful is that the get method comes with several parameters, most notably the parameters IDs and include. Pass any IDs in the list as a value to the first one. I'll quickly copy-paste one. As a value to the second parameter, pass a list storing the string embeddings. Upon running the cell, we obtain the vector representation of the chunk with the specified ID. Cool. It's now time we learn how to add a document to the database. Create a new variable called addedDocument and set it equal to the following document object. You might recognize it as the first element in the pages character split list that I copied from the notebook for the last lesson. Now we wish to add this document to the vector store. To do so, apply the addDocuments method to the respective object. Pass a list storing the document as an argument. Upon running the cell, we add the document to the vector store under the following ID. To double-check, let's apply the get method to the vector store object, specifying this new ID as an argument. As expected, we retrieved the document. All right, let's now update it with a document from the second lecture. Configure a new object called Updated Document. Set it equal to the last document in the page's character split list, index 19. Now, update the previously added document by applying the relevant method on the vector store. The parameters we must specify are document ID and document. Pass the ID of the document that needs updating as a value to the first one. The second value must be the document that will substitute it, namely, updated document. Did anything happen? To check, let's apply the get method again and pass the ID as an argument. Excellent! The process has been executed successfully. The next and final method we'll cover is deleting an object with a specified ID. It's not difficult to guess how that process should go. In a new cell, type vector store from directory .delete and pass the familiar ID as an argument. Now apply the get method and ensure the ID and corresponding document are no longer part of the vector store. Indeed, a document with the specified ID doesn't exist. Well done, everyone! With that, we've exhausted the indexing part of the RAG technique. Next on the agenda is discussing the retrieval process, which includes retrieving documents relevant to a user's query. Can't wait to explore this topic with you in the following lesson. Welcome back, everyone! Last time we learned how to access and manipulate documents in a vector store, marking the end of the discussion on indexing. The upcoming lessons are dedicated to the next steps in the RAG process, retrieval and generation. We'll demonstrate two of the many algorithms available for retrieving documents, the similarity search and the maximal marginal relevance search. Finally, we'll introduce LangChain's vector store retriever object and its advantages. All right, there's a lot to cover, so let's not waste any time and jump straight into coding. I've created a new Jupyter notebook where you can find a short, pre-implemented code, including the familiar magic commands, the importing of the OpenAI embeddings, chroma, and document classes, and the definition of the embedding and chroma object. In addition, I've included the following chunk to the vector store, creating a duplicate in the database. You'll see how this will affect the results later. Now, our goal with this lesson is the following. First, define a question related to data science. Secondly, use the embedding function of the vector store to create a vector representation of this question. And thirdly, retrieve a pre-selected number of documents relevant to this question. At the next step, these retrieved documents will be fed to an LLM to devise a response. So let's create a variable called question, defined as follows. What programming languages do data scientists use? Let's first find out what chunks of text would be relevant to the question. If you skim through the lectures in the docx file, the first one discusses the differences between the terms analysis and analytics. The second one covers various software and programming languages that data scientists typically use in their work. Therefore, we expect the results to belong only to the second lecture. Now let's quickly identify the programming languages mentioned in the text. The first relevant reference includes the following. As you can see from the infographic, R and Python are the two most popular tools across all columns. Next, we find a sentence noting R and Python's limitations and mentioning SQL as one better suited for managing relational databases. Later in the text, we see the following reference to MATLAB. When it comes to data science, mentioning MATLAB is inevitable. It's ideal for working with mathematical functions or matrix manipulations. Toward the end of this discussion, the author also mentions Java, JavaScript, C, C++, and Scala. Very good. Now that we know the relevant text chunks, let's use Chroma's similarity search method to see if the results we retrieve meet our expectations. Create a new variable called retrieved documents and set it equal to vectorstore.similaritySearch. The first parameter we must pass is query, our question. The second parameter to set is k, corresponding to the number of retrieved documents. It defaults to 4, but let's change its value to 5 documents, allowing us to identify a pain point in the similarity search algorithm. Displaying the variable, we find that retrieved documents is a list of 5 documents. I find this a bit difficult to read, so let me use a for loop that displays only the page content and the lecture title of each document. Much better. We first see that all 5 chunks are extracted from the second lecture, as expected. This is a great first impression of the similarity search method. Next, after studying the content, we find that the accent in the first chunk falls on the Java and Scala programming languages. The second chunk references Java, JavaScript, C, C++, and Scala. The third chunk emphasizes R and Python as the most popular among data scientists. We can also see MATLAB included in one of the chunks, but not as the main character. All right, the similarity search method has performed exceptionally well so far. Looking at the fourth document in the list, we find the algorithm has retrieved the chunk storing the lecture's introductory sentences. But recall that this is the text we duplicated earlier in the code. Consequently, the similarity search method retrieves this document twice, the original and the duplicate, since both come with the same similarity score. It turns out the method is not sophisticated enough to recognize one of these retrievals as redundant. This poses an issue since this fifth chunk could have contained new valuable information rather than repeating an already retrieved one. Fortunately, there's a way to overcome that. In the next lesson, we'll study another technique Chroma offers, the maximal marginal relevance search. See you shortly. Welcome back, everyone. In the previous lesson, we employed Chroma's semantic similarity search algorithm and found that it performed quite well in retrieving content relevant to a user's prompt. It did, however, come with a disadvantage. If a vector store contained duplicate documents with a high similarity score, the method would retrieve both the original and the duplicate. And as we'll now discover, retrieving documents based only on the similarity metric results in a lack of diversity and a chance of missing important information. In this lesson, we'll study another retrieval algorithm that accounts for this shortcoming. It goes by maximal marginal relevance search, or MMR search for short. Let's jump right in. In our last lesson, we focused on the second lecture and worked with the following user prompt. What programming languages do data scientists use? The similarity search method retrieved answers mentioning R, Python, MATLAB, and other programming languages popular among data scientists. Change this question as follows. What software do data scientists use? Skimming through the docx file again, we find that the software mentioned are Excel, SPSS, Apache Hadoop, among others highlighted on the screen. Let's keep this information in mind as we proceed. Returning to our Jupyter notebook, apply the familiar similarity search method to retrieve documents relevant to the query, restricting k, the number of documents, to 3. Use the familiar for loop to print out the page content and metadata of the documents. As expected, all chunks originate from the second lecture. After studying the content, we found the first document contained information on the R and Python programming languages, which was irrelevant to the current question. The other 2 documents are the original and duplicate chunks that don't reference any of the software mentioned. It seems like the method missed important information hidden throughout the text. Let's therefore introduce the maximal marginal relevance search. This algorithm aims to find the balance between fetching documents relevant to the user's query and retrieving documents that are less redundant concerning already retrieved ones. As we know, a document's relevance with the query is determined by the similarity score between the two. The higher the score, the higher the relevance. A document's redundancy score, in turn, is found by calculating its similarity with all retrieved documents, and then taking the highest among these values. A higher number indicates that the document is less likely to contribute with new, unretrieved information. Let's change the sign of the redundancy metric from positive to negative, and call this new one diversity. The linear combination between relevance and diversity is called marginal relevance, as coined by Carbonell and Goldstein in their 1998 paper. The parameter controlling the balance between the two metrics, or the prevalence of either, is conventionally denoted by lambda and takes values between 0 and 1. Let's multiply the relevance component by lambda and the diversity component by 1 minus lambda. We can infer that a value of lambda closer to 0 diminishes the first component and puts more emphasis on diversity. On the other hand, a value closer to 1 reduces the diversity among the retrieved documents, concentrating more on relevance to the query. Therefore, if we vary this parameter, we're effectively choosing which is more important to us, how relevant or how diverse the answers are. Okay, enough with the theory, it's time we see it in action. Return to the notebook and replace the similarity search method with a maximal marginal relevance search. Leave the parameters query and k unchanged. Another parameter this method offers is, as you might suspect, the lambda multiplication factor. Let's explore its extremes by setting it equal to 0.1, favoring document diversity. Run the cell and then the for loop. We discover the familiar document referencing R and Python, the closing remarks of the same lecture, and a paragraph from the analysis and analytics lecture, which seems quite irrelevant. Indeed, the results turned out to be a bit too diverse for our needs. Now is a good time to introduce another parameter available for both search methods: filter. Let's instruct the method to retrieve chunks only from the second lecture in the docx file. To do so, create a dictionary, set the key to lecture title, and set the value to the title of the second lecture in the document. Then rerun the code. We see that 2 of the documents have been retrieved again, but the document from the analysis and analytics lecture has been replaced with one from the required lecture. It's also quite relevant to the question, referencing software like Apache Hadoop, Apache HBase, and MongoDB. All right, let's see the effect of increasing the lambda parameter to, for example, 0.7. The first and last documents are retrieved again. The second one, however, has changed to a chunk that references Hadoop, Power BI, SAS, Qlik, and Tableau. Finally, let's remove the effect of the diversity component altogether by setting the lambda parameter to 1. We get a familiar result: 1 document referencing R and Python, and 2 identical others. Recall that this was our result when we ran the similarity search method earlier in this lesson. A lambda value of 1 removes the diversity component altogether, leaving only relevance. All right, I suggest we stop the lesson here. In the next lesson, we'll continue our discussion on retrieval. We won't introduce other retrieval algorithms, but instead demonstrate how to create a runnable retrieval object. See you there! Hey everyone! So far, we've introduced 2 retrieval methods: the similarity search and the maximal marginal relevance search. These methods did an excellent job of retrieving information relevant to a user's query. But they aren't expected to work flawlessly in all use cases, and there's always room for improvement. If you navigate to LangChain's documentation, you'll find many retrievers suitable for different tasks. We won't study these retrievers individually. I'll leave it to you to find the one that works best for your project. Rather, we'll create a runnable retriever object to plug it in as part of an expression language chain. On the screen, you'll find a piece of code that fetches the documents and embeddings from the locally stored database. As before, there are 21 documents, 20 unique and 1 duplicate. Pause the lesson, implement this code in your notebook, and run all cells sequentially. Now create an object called retriever. Set it equal to vector store.asRetriever. One of the available parameters to this method is search type, and it defines the type of search that the retrievers should perform. As the documentation instructs, we can choose between the following: similarity, MMR, or similarity score threshold. We haven't discussed the latter in detail, but it simply applies the similarity search with an additional minimum relevance threshold. Let's opt for the familiar MMR search. The next optional parameter is search keyword arguments, which allows us to set parameters specific to the chosen search algorithm, such as K, lambda, filter, and others you find relevant. Given that we've chosen to work with the MMR search, we can specify the number of documents retrieved, K, and the lambda multiplication factor. Create a dictionary with 2 key value pairs. Set the number of documents to 3, and then the lambda parameter to 0.7. Run the cell and display the retriever object. It's an instance of the vector store retriever class. If you trace the hierarchy, you'll find that it inherits from the runnable class. Okay, let's retrieve some documents, shall we? Define the following question. What software do data scientists use? Recall that all runnable objects implement the invoke methods, so let's define a new variable called retrieved documents as retriever.invoke, passing the question as an argument. Since retrieved documents is a list of document objects, we can apply the familiar for loop and format the retrieved chunks. Very good! The invoke method returned the same chunks we got when applying the MMR search method in the last lesson. So, we have all the components ready to create our first retrieval chain, allowing us to present the final bit of the RAG technique, generation. Join me in the upcoming lessons, where we'll discuss just that. Hey, and welcome to this lesson, where we'll implement the last step of the RAG technique, the generation step. We'll create an expression language chain from scratch that uses the documents returned by the retriever to generate a context-specific response. I've pre-implemented only the environment variable setup and the necessary imports for this lesson. Feel free to pause the lesson and transfer this code to your notebook. First, let's create a vector store object using the Intro to Data Science Lectures folder. Ensure it keeps 21 documents in total. Next, create a vector store backed retriever by applying the asRetriever method to our vector store. Specify the search type as maximal marginal relevance. Then assign the parameter search keyword arguments to a dictionary, setting the number of retrieved documents to 3 and lambda to 0.7. We've now created a retriever object that implements the invoke method. Great! Let's now define our prompt template from a string template. At the beginning of the string, we require the user's question. Next should come the context from the retriever. Finally, we end the template with instructions to specify the resource. The next step is to create an instance of the prompt template class, apply the fromTemplate method, and pass the string as an argument. Next in line comes the chat object, defined just as usual. Finally, let's create a variable question storing our input. What software do data scientists use? All right, we have all the components ready to construct our chain. Let's do so systematically, invoking one element at a time. We start by constructing a dictionary storing context and question as keys. The values are the text that will be entered in the prompt template. Let's start with the question that must enter the prompt template unmodified. We achieved this with the runnable passthrough class. The context should, in turn, be set to the retriever object, which, upon invocation, returns the list of relevant documents. Very well, let's invoke the chain created so far and inspect the output. We've hit an error. Dictionary object has no attribute invoke. Note that since the dictionary isn't piped to any other runnable, we cannot apply the invoke method on the chain. Recall that the remedy was to pass it as an argument to a runnable parallel class. Let's give this another go. Sure enough, we obtain a dictionary with context corresponding to 3 retrieved documents and question being the unmodified user input. Excellent. Continue constructing our chain by piping the prompt template next, which will accept this dictionary as an input. Now that we have the first component piped to another runnable, wrapping it inside a runnable parallel is no longer necessary. This way, we make our code cleaner and save ourselves one class import. Let's invoke this new chain, shall we? The result is a string prompt value instance storing the filled-in string template. Let's copy the text and paste it as an argument to a print function to see more clearly what the template looks like. The input variables question and context are successfully substituted with their respective texts. Perfect! I think we're making great progress. Feel free to take a short break before entering the next code along, during which we'll continue building our chain. See you shortly in this section's final lesson. Welcome back! We've made significant progress in constructing our retriever chain. So far, we've piped a dictionary with the prompt template. Recall that we obtained a string prompt value instance, which stored the filled-in prompt template. Now, let's continue the implementation. The next component we pipe to the chain is our chat OpenAI instance. Redefine the chain accordingly and invoke it again. We obtain an AI message object where the content parameter stores the text generated by the model. We can copy-paste it inside a print function for better inspection. Indeed, the model considers the retrieved context and has also remembered to include the resource. Excellent. What's left is to introduce one final component, an instance of the string output parser class, which converts this AI message object to a simple string. Invoke the chain one last time. Perfect! All right, everyone, I hope you've learned a great deal about the individual RAG components and how they combine to create a retriever chain. As a final remark, inserting all retrieved documents into the prompt is called stuffing. As I hope you've seen, stuffing is a straightforward, easy-to-implement approach that would result in excellent model responses in most cases. But it wouldn't be a suitable choice when, for example, the number of documents or their content is so extensive that it doesn't fit the context window limit of the model. As an additional drawback, research shows that models primarily use information at the beginning or end of a document list. Therefore, information in the middle of the retrieved list may be disregarded by the model, regardless of its importance. One method alternative to stuffing is document refinement. This technique solves the problem of context window limits by passing the documents to the model one at a time. When an answer is generated, it's passed to the model with the next document in the list and the developer's instructions, thereby updating the old response with the additional information it has received. When all documents have been fed to the model, the answer should account for each piece of information. Of course, contrary to the stuffing technique, this method comes at the cost of passing many more calls to the LLM, making it more expensive. Okay, we can confidently pat ourselves on the back for our great work. Throughout this section, we took the time to study each element of the Retrieval Augmented Generation technique, from loading a document, to splitting into chunks, to embedding them, to storing the embeddings in a vector database. Finally, we created an expression language chain that retrieves only the documents most relevant to a user's question and formulates a context-aware response. We'll meet again in the final section of this course to discuss another exciting topic: tools, toolkits, and agents. Catch you later.